So this is our second example of a type of problem that we can solve using differential equations. Kind of problems we call mixing problems, and this one is more of a classical example of a mixing problem in that you have things that are being mixed here. So a tank contains 100 liters of salt water at a concentration of 15 grams per liter. Water containing 23 grams per liter of salt is pumped in at 3 liters per minute, and the resulting solution is pumped out at the same rate. How much salt is in the tank after 1 hour? So what we need to remember here is that in mixing problems, we are always going to model this thing as this basic differential equation. dy dt, which is the amount of something, is going to be the rate at which that something is going in minus the rate at which that thing is flowing out. And the thing that we are interested in this example is the amount of salt. So we're going to set up our differential equation. We're going to let A be the amount of salt in the tank. So the differential equation we're going to have is dA dt is equal to the amount of salt that is coming into the tank minus the amount of salt that is flowing out of the tank. So let's come up with expressions here for the amount of salt coming in and the amount of salt coming out. So if we want the amount of salt coming in, remember the amount of salt is going to be measured in grams. So we are given some information here about the volume of the tank. We are told the concentration of salt water. We're given another concentration of salt water coming in, and we're given the rate at which water is coming in. So if we want to calculate the amount of salt that's coming in, we want to figure out, we want to take the volume of water coming in times the concentration of salt in that water. So we're told that the water is coming in at 3 liters per minute, and it has a concentration of 23 grams per liter. So if we just look at the units here, we've got liters per minute, we've got grams per liter. If we multiply these two things together, the liters, top and bottom, are going to cancel out, and we're going to be left with the rate at which salt is coming in, 69 grams per minute. So the rate at which the volume is coming, the rate at which the water is coming in times the concentration of salt in that water. Same sort of analysis for the rate at which salt is coming out. Okay. We have it flowing out again at 3 liters per minute. And the concentration of water, of salt in the water that is flowing out, well, this is what we don't know. Okay. It's going to be some concentration here, and this is a bit of a mystery, because this is going to depend on how much salt we have in the tank at any point in time. We assume that the rate at which the salt is flowing out of the tank, or the concentration of salt in the water flowing out of the tank, is the same as the overall concentration of water in the tank at any point in time. So concentration, I'll just say here that this depends on A, which is the amount of salt in the tank. So how can we express this concentration mathematically? Well, let's just remember we've got this rate, we've got 3 liters per minute here, this volume flow. If this concentration here is the concentration of salt in the water in the tank. We know that the amount of water in the tank is A, measured in grams, and we know that the volume of the tank is 100 liters. So we can express that concentration as A divided by 100. So when we multiply this to get the rate at which the salt is flowing out, we're going to get 3A divided by 100. And again, our liters are going to cancel out. And that's going to give us grams per liter because the amount of salt is measured in grams. So we can take these two things and we can put them together into the differential equation that we're trying to solve. So we'll do this on another page here. Our differential equation is dA dt, and then we want the rate at which salt is flowing in. That was our 69, minus 3 over 100 times A, which is our rate at which things were flowing out. So I'm just going to, and now basically this is the differential equation that we want to solve here. So how do we solve this thing? Well, let's start by getting a common denominator here. So we'll have dA dt, and we'll get a common denominator of 100. So this is like 6900 minus 3 all over 100 all times A. So I'm kind of grouping all of this stuff together here in terms of one factor on my A here. And then what I'm going to want to do is I'm going to want to, maybe I didn't want to do that step. That's going to make this a little trickier. So let's just rearrange this a little bit. Let's actually bring the A in here. So it's going to be, let's rewrite this a little bit as, that step isn't going to work, is it? Yeah, that makes no sense because that implies that the 6900 is divided by the A. So let's change this here a little bit. Let's still get our common denominator. So this will be the 6900. Okay? And we'll write this as minus 3A over 100. Okay, that looks a little bit better. That's just getting a common denominator between the two terms. And then let's divide everything through by this 3, because we don't want this little coefficient here on the A. So we can rewrite this as 2300 minus A over 33.3. Repeated. Okay, just dividing through by top and bottom by 3. This means that, well, and this is still all equal to dA dt. And the whole point of doing this is to get these two fractions, a single numerator on one side, a single denominator on the other side. So now we can turn this into, this is now a separable differential equation. We can take this whole thing here, this 2300 minus A, and we can move it over to the left-hand side. And, oh no, sorry, it's going to be in the denominator when we move it over. So this side is going to be dA over 2300 minus A. And then on the right-hand side, we are going to have 1 over 3300, 33.3 dt. And then we want to integrate both sides. So how do we do this integration here? Well, on the right-hand side, we've got 1 over something with an A in it. So my derivative here is just going to be, I know my antiderivative is going to be ln of the absolute value of this thing here. And I have to make it negative because the A in here is negative as well. Over here, what can I do with this thing? Well, this 1 over 33.3, of course, is just 3 over 100 dt. So let's write this as, 0.03 t, and we'll factor in a constant of integration here. Now, how do we evaluate this constant of integration? Well, we know that at t equals 0, the amount of salt in the tank is the concentration, 15 grams per liter, times the volume, 100 liters. So the amount of salt in the tank initially was 1,500 grams. This is, again, concentration times volume. So if we sub in t equals 0, we get negative ln 2,300 minus 1,500 is going to equal C. So negative ln 800 is going to be our constant of integration. So what are we trying to find here? Well, we've got our equation here. We can sort of put all this together. Negative ln 2,300 minus A equals 0.03 t minus our constant of integration, ln 800. Okay. We want to come up with an equation for A as a function of t. So let's start by dealing with this negative sign over here. Okay. So we'll make everything over here negative. 3t plus ln 800. And then let's raise both sides to the exponent, to the base e here. So that'll get rid of the ln on this side. And this side over here will be e to the negative 0.03 t plus ln 800. So removing the absolute values here, we're going to get 2,300 minus A equals, and the e and the ln are going to kind of cancel each other out, and we're going to get 800 e to the negative 0.03 t. And then we can just rearrange to solve for A. A is going to equal 2,300 minus 800 e to the negative 0.03 t. Okay, so we've got an expression for A, which is the amount of salt in the tank, as a function of t. So where do we want to go after this? Well, we wanted to find the amount of salt in the tank after 1 hour. So t here has got to be in minutes, so we'll just say after 1 hour, t equals 60, because this is in minutes, and so we can work out what this is. Our amount is going to be 2,300 minus 800 e to the 0.03 times 60. Punching this into our calculator, we get approximately 2,170 grams.